can continue, then just press next. And then we are going to crystallography external form. So, and then we are going to, we have a very stop yesterday. Yes, we started yesterday with this one. We did the symmetry operations. Yep. And we did this one, the local inversion axis. Yes, this one. Yeah, then this one, yes. So, and now we are going to the center of symmetry, yes. So, then you can just make a double click on this one, or I can do it as well. So we have phase inversion, then we have the object inversion, and we have a point inversion. So in these inversions, they are going always through the center of the symmetry. So now we will check how this looks like. This is not working. And this is a magic touch here. So, yeah, it is not working at all. So, because you have then the wrong movie player on it. Then we just connecting this again, and if it is then still not working, then we are going home. Yes, it is not working, yeah. And next time I will bring then again my old Mac, yeah. So then let us check what happens here now. Aha. So now we have here something, yeah. We have the thing, but that is just an so then we are going here, then we are going here. Yes, then we are pressing here, just continue. Next. So then we are going to crystallography external form. So, and then we are going to symmetry operations. So, and now continue. And now we are going to the center of symmetry. So, and now we are making a double click to the phase inversion. Yeah, finally, nobody can believe this. Actually, the university should pay you guys for all these punishments. So now we have a crystal with the center of symmetry, yes, and the center of symmetry that is here in the middle. And then we can, of identical phases, yeah. So, and then the animation will point out how we are running here around the center of the symmetry. So here we have the center of the symmetry, and here we have the three axes, and these three axes again along A, B, C. So and now we are moving our crystal around the center of the symmetry. So and there you will then get or generate equivalent points on the parallel surfaces. So and this goes always through the center. So in the center, that is then always and that is always the center, yes? And then you can put here a crystal inside, and one can observe that it is turning always around the center. So, and then we can have an object inversion. So, and here we have just our object, and then we will just move our object here on the other side. And that is point by point. So and now we are done with our object, and our object is then here on the other side, and it is then the other way around, like on the mirror surface. Moment, I forgot there something. So here it is written again. You will then get the equivalent objects, and your x, y, z points is then on the other side with a negative sign. Yeah? You have minus x, minus y, minus z. And if you are replacing here a, b, c, it depends always on the orders. Then we have here x, we have here z, and then this here is the y. Or we have the point inversion, and the point inversion, that is then, as we are calling it, that is just one single point plotted on the other side. So we can now plot the point. So and then we are moving just our point inwards through the origin. Yeah, here it is not happened by itself. Then we are just plotting our point here on the other side. So, and you know this from school when you have done your math class, yeah? If you have, there you have used the Cartesian coordinate system, and then you could also plot points from one to the other side. So, and then you got also then a negative sign, yeah? So, but here we are moving then in 3D, and in your math class in school you have just used two axes, the x and the y axis. So now we have we talked about all the symmetry operation, the rotation axis, the mirror planes, the roto-inversion axis, and the center of the symmetry. Are there any questions? I don't think so, because it's very easy. So just use them, or just get from Neil the software that you can go once more through this CD and check it. So then we have the crystal classes. So and we have different crystal classes. We have all in all 32 crystal classes, and these or point groups, and you can describe every crystal which you can find here on this planet will fit in one of these 32 crystal classes. Yeah. So and there you have then certain symmetries, certain rotation axis or roto-inversion axis, mirrors, and the center of the symmetry can then be used or will be used to describe these 32 crystal classes. So in these 32 crystal classes, they can group into 6 crystal groups. So and there is actually the thing where we like to go. We have a triclinic system, we have the monoclinic system, you have the orthorhombic system, tetragonal system, hexagonal system, and the isometric system. So within these 6 systems, there is always one crystal class with the highest symmetry content for that system. So I mean that is just actually the description, and let us go now to the movies and check it, how it looks like. So this table is now important. So we have here a triclinic crystal, we have a monoclinic crystal, orthorhombic crystal, tetragonal crystal, hexagonal crystal, and isometric crystal. So and here we have then the characteristics, then we have here the crystal systems. I mean, these are again here the different crystals, and we have the crystal class. Here we have a 2M, 2 through M class, 2 to 2, M2, and so on. So, and these are actually the first letter that describes always then the crystal system. So and the M that describes, for example, then if we have a mirror, yeah? So in the second we have here 2, 2, 2, that means we have 3 rotation axes. We have three rotation axes, and these 3 rotation axes are 180-degree rotation axes, yeah? So and here is then the characteristic of the symmetry. We have here 1 2-fold rotation axis, that is this one, yeah? 1 2-fold rotation axis and or 1 mirror. So here we have 2 2 2, 3 mutually perpendicular directions about there is a binary system, 2 or M. So and these 2 stands then for the 2-fold rotation axis, and therefore we have 3 2-fold rotation axes, and they are perpendicular on it. And I told you, for example, when we discussed the orthopyroxenes, that the angles between all these 3 axes here are perpendicular. That means alpha, beta is gamma, that the angles are all the same, and this angle is the 90-degree. So and then we have here again the M, and the M, these are the mirrors. If we have 2M, then we have 2 mirrors, yeah? So here we have 4 that stands for tetragonal. That means we have 4-fold axis here. So and if we have here the line over the 4, then we are talking about the roto-inversion axis. So and here we have 4 over M, then we have a mirror, yeah? So these are the different classes which can occur in this system, yeah? This is one class, that's the other one, that's the other one, and that is the next one. Then we have here 4 2 2, for example. That means we have 1 4-fold rotation axis, 1 2-fold and 2 2-fold rotation axis, or we can have in the tetragonal system 1 4-fold rotation axis and 2 mirrors. Yeah, the M is always the mirror, and the number that is it describes if we have a 2-fold rotation axis or a 4-fold rotation axis, yeah? So and here we have the hexagonal system. We can have a normal hexagonal system with a 6-fold rotation axis, or we can have a hexagonal system showing 1 6-fold rotation axis and 2 two-fold rotation axis, or we have 6 mm, that means we have one 6-fold rotation axis and 2 mirrors. So and now let us just figure out how this looks like in nature or when we are checking a crystal. So here we can we click? Yes. So here we are in the triclinic system, yeah? So and if we have the triclinic system, then the angles between our axes here, that is the beta, that is the alpha, that is the gamma, this is not the same, yeah? You have here everywhere different angles, yeah? So and then we no, these are the axes. A is not B and is not C. So the lengths of our axes are not the same, yeah? So and the same for the angles. Alpha is not beta and alpha is not gamma, and beta is also not gamma, and it is also not 90 degrees. So and if you have a tricline crystal and you are checking this tricline crystal, then it will not, the elongation when it becomes dark is then not aligned to the north-south or east-west axis under the microscope, yeah? Because all the axes have different lengths and the angles are also different, yeah? So now going through here, in this system, crystals are referred to 3 crystallographic axes of unequal lengths that makes oblique angles with each other. Yeah, I mean, if you have here, if all the axes are of different lengths, then consequently the angles are different. So, and that is now the triclinic system. So and now we have here the next numbers 1, 0, 0, 0, 0, 1 and 0, 1, 0. These are the Miller's indices, yeah? So and if we are putting our Miller's indices here, then that is 0, 0, 1, 0, 1, 0, 1, 0, 0. So, and that is now the triclinic system, which we are just, if we are writing down this thing, then it is just a 1, yeah? Because if we are turning this crystal, then we have to turn it 360 degrees, that we can produce a tally, yeah? That it overlaps itself. So you have a tricline crystal, you have to move around 360 degrees. And I showed you this just yesterday by using these different figures. And there you could see that you can produce only the tally by moving this crystal 360 degrees around. So then we have here the axis A plus. If you are going to this side by a symmetry, by an inversion through the center of symmetry, then we have here the minus, yeah? The minus A. So here we have C plus, then we have here the minus C. Here we have B plus, then we have here the minus B. So because your crystal is always moving around here along the center of symmetry. So and the next possibility what we can create in the triclinic system is here I don't know how this is called in English, you know, this line over the 1, yeah? But you can see it. So and now we are clicking there. Here you have again our A, B, C and the alpha and the beta and the gamma. So and here we have now the rotation. So here we have, that's the crystal, and then you have the A-axis here, yeah, that goes here through the crystal like this. Here you have A plus, here you have A minus. Then we have the B-axis going here through the center of the symmetry, B plus, B minus. the C axis going along here, that is the blue one, we have C and C minus. So totally, that is how the mineral looks then in nature, or that is one typical tricline mineral, and that is here the mineral called axinite. So then we have the rotation about C. So and if we are rotating it about along C, yes, that is the C axis, then it is rotating like this. And sorry for that the images are so dark. Can one see it from here? Yes, one can see it. So and then you are rotating here along C, or we can make a phase inversion. So then you have here the different phases, and then you are putting just the different phases. Here we are starting with this point through the center of the symmetry to this side, yeah? All the different, all the points at the different edges. So and then you are producing everywhere the C to the C minus, and the A to the A minus, and the B to the B minus. So what is now for you as an ES203 student important? That is, you should know that we have a tricline crystallographic symmetry, and that A is not B and B is not C, that you have the lengths of your axes differ everywhere, and therefore the angles are also differ everywhere. So, and if you are doing your microscopic work, and you have some idea about the symmetry, then you can make a much more, you can close up your view much more, and then you can make some estimation. That could only be this mineral, because the elongation is not a line through the north and the south and the east and the west in your microscope. So that was now the tricline system, and in the tricline system we can have two symmetries. That is here the one, or with a very little symmetry, the slash over 1. So then we are going to the monoclinic. So in the monoclinic system, there we have also the length of the axis is also different, but beta is over 90 degrees and alpha and gamma is 90 degrees. Yeah? So in the typical mineral within the monoclinic system, I told you this before in class, that is the dioxide. Yeah? So whereas the N-star type is orthorhombic, because you have only magnesium and silica cations. I mean on the N side you have only the magnesium, and on the tetrahedral side you have only the silica. But if we are talking about the dioxide, then we have calcium on the N side and magnesium or iron on the N side. And due to the fact that these bubbles have different radius, then you are changing the symmetry, and beta becomes then more than 90 degrees. So and there we have 3 crystal classes in the monoclinic system. We have the 2 over n, the n and the 2. So and as I told you, the 2, that is a 2-fold rotation axis perpendicular to the mirror plane, is usually taken as the b-axis. The c-axis is always vertical, and the a-axis is inclined downward toward the front. So So and now we are going here to the 2 over m. So now at first the total symmetry. Here we have a typical mineral which shows in the monoclinic system. There we have gypsum, yes? And you know gypsum, it is also lying somewhere around here. No, it is not. So here we have the perspective view. Then we make now a rotation about B. So and the B axis is this one, yeah? So and that has a two-fold rotation axis. That means we can move the crystal faces, or we can repeat them 2 times in 360 degrees. That is just the two-fold rotation axis. So then we are going now to a rotation about C. So then a rotation about 3 we have a one-fold rotation axis. Yeah, we are turning it now along here. So and there we have to, the crystal faces will repeat 1 time in 360 degrees. So and that is then the 2 over m. So now let us go to the orthorhombic system. So if we have the orthorhombic system, then A is not B and is not C, but alpha is beta and is gamma. That's always the same angle, and that is 90 degrees. So the crystals in this system are referred to 3 crystallographic axes of unequal lengths that make angles of 90 degrees with each other. Here you have again A plus, A minus, C plus, C minus, B plus, B minus. So and in the orthorhombic system, the longest axis is commonly chosen as the C axis. Yeah? However, in the orthorhombic crystals with platy habit, the C axis turns out to be the shortest of the 3 axes. The crystal classes that are part of the orthorhombic system is 2 over m, 2 over m, 2 over m, or m2 and 2, 2, 2. So then we have rotation for 3 crystal classes refer to the symmetry elements in order of A, B, C. That is then these two classes, and the two-fold rotation axis coincide with the location of A, B, C. For example, then the MM2, we have then 1 two-fold rotation axis. There we have here written only 1, 2, but we have 2 mirrors. And now we will just check how this looks like. At first we are going to the MM2. So at first let us check the total symmetry with the photo. And here we have an hemimorphite. Yeah, nobody has heard about a hemimorphite by now, but now you got it as well. So, but anyway, you can even see in the crystal that we have here, these angles here between the edges is the 90 degree. So then we have perspective, and then we have the rotation about C. Here we have our C axis. So, and we have here a two-fold rotation axis at the intersection of two mirror planes. So we can run it along here, that is then the two-fold rotation axis, and then we have a mirror plane here, and we have a mirror plane here, yeah? So that is our two-fold rotation axis. Yeah, we can repeat the whole thing 2 times in 360 degrees, and we have our two mirror planes. So that is then the MM2. So now, by now you should get the first idea how these crystallographic classes are described. You have your mirror planes and the rotation axis. Yeah. So now let's go back, and then we will now check the 2 over M. So there we can now do a little bit more. Yes, we have the rotation about A, we can rotate it about B, and we can rotate it about C. So let us just figure out what we have here for a nice picture. Here we have a baryt, that is a barium sulfate. And then we have the rotation about A. So this is then the A axis is here, and we have a two-fold rotation axis and a mirror plane. So, and there we are now turning it around there. Here we are turning it. So, and then we can repeat the phases 2 times in 360 degrees, and then we have a mirror plane. We have here one, and we have here one, yeah? Yep. So, and we have 3 times 2 over M, because we have the same rotation about B and the same rotation about C. So then let us just check here. So now we are rotating it here around B. Yep. So, and there we have then the next two-fold rotation axis, and we have the two mirrors, here and here. And last not least, the whole thing along C. Then we have it here we have the C axis. Now we are rotating it again, and then it looks like this. So, and again, the two-fold axis and the mirror planes. Here you have a mirror, here you have the mirror, yeah? So, and that is then actually just a playing around. Normally we should have as teaching material all these crystallographic classes, you know, in such wooden objects. So this was then the orthorhombic system. So now we are going to the tetragonal system. And in the tetragonal system, that looks then different. We have here A has the same length as B, but C is not equal with C. So in the angles between, that is always 90 degrees, because therefore we are in a tetragonal system, yeah? So, and here we have a 3 crystallographic, or we have a 4 over M, 2 over M, 2 over M, then we have 4 with this line on the top, 4 to M, 4M, 4 to 2, 4 over M, 4 with this line, and 4. So, and of course, there we have then always, in the tetragonal system, we have always a 4-fold rotation axis, and we can have 2-fold rotation axis, and we can have mirrors. So should we just finish with this one, or do you have something else? Okay, then let us just go to the 4 over m. So here we have the 4 over m, and here a picture of the total symmetry with photo. So, and here we have, for example, the scheelith, and that is a tetragonal D-pyramide. And there, with the 4 over m, we can rotate it about c, that is here the c-axis. So, and then we are okay, and then of course we have a 4-fold rotation axis perpendicular to a mirror plane, yeah? And we can repeat the crystallographic phases 4 times in 360 degrees. So this is now repeated 4 times in 360 degrees, and the mirror plane we have here, yeah? Here we cannot have it because here we have this edge. So there we have the mirror plane, and we can repeat it 4 times in 360 degrees. Then we have 4 with this slash on it, 2 over m. So there we can make a roto inversion, and that is always if you have the line on the top, that is the sign then for a roto inversion. Yeah? Then we need the total symmetry with the photo, and here we have a chalcopyrite. So in the you should be familiar, or you have heard about the chalcopyrite. Chalcopyrite is a copper iron sulfide, and that occurs also in close to Nandi, in this where they are doing copper exploration, or where they have at least done it. So then we are making the roto inversion. That is here the 4 over, yeah. So we have here a 4-fold roto inversion. That means we are rotating it here along C. And of course you can reproduce it 4 times in 360 degrees. -90-degree rotation now, yeah. Then we are making the inversion, and the inversion is always through the center of symmetry. Then we are rotating it again 90 degrees, then we are making the inversion. Then we are rotating it again and making again the inversion. And finish. So, and then we have the rotation about A. So, and here we have, there we have a 2-fold rotation axis, yeah. And the crystallographic system was, which was written down, that was the roto inversion. Then there was a 2, that means we have a 2-fold rotation axis, and then it was 4, 2, m, and then we have also somewhere a mirror plane. Just check it. Yes, now we have repeated it 2 times in 360 degrees. No, that was 4 over, yes, 4, that was which one? This one, yeah? So, and then we can stop for today, yeah. And I will then upload through the weekend an example how the test looks like, yeah. So that it's not the same, but only that you're getting an idea how it looks like, yeah.